Now we're getting to a really tricky problem, and I will say that the reason we're doing this problem is because this class is called pre-calculus, and this is a problem that might show up in calculus. So I'll show you how to do it. I'll explain why it's useful in calculus, and I'm sorry for those of you who may never do calculus, but that's part of the class, is we have to get prepared for that. So this is asking me to rewrite y equals tangent of inverse cosine of x as an algebraic function of x. And I want to look back up and say this is very similar to the problem number 4 that we just did. We never needed to actually know what the angle was. We just had to look at the ratio of the sides and figure out, use the Pythagorean theorem and figure out a different ratio of the sides. We had 2 sides, found the third side, and then used a different ratio. It's exactly what we're going to do in example 5, except we don't have specific numbers. So I'm going to start out by looking at this tangent of inverse cosine, and remember we take inverse cosine of a trig value in order to find an angle. So x is a trig value, so I'm going to write it as a ratio of x over 1. So this is telling me that my adjacent side is x, and my opposite, or my hypotenuse is 1, which reminds me very much of the unit circle, doesn't it? So the first thing I'm going to do is draw this angle. Now the problem is I don't know whether it's positive or negative, because cosine x could be a positive number, x could be a negative number, and so this triangle, or this angle I draw, could be in quadrant 1 for inverse cosine, or it could be in quadrant 2 for inverse cosine. So I'm going to write down here if x is greater than 0 and if x is less than 0. So if x is negative, I would be in quadrant 2. If x is positive, I would be in quadrant 1. So I'm going to draw a little triangle, and I'm going to label the adjacent side as x and the hypotenuse as 1. Now notice I'm not calling this negative x, I'm just calling it x if x is less than 0 and x if x is greater than 0, because x could be a positive number or a negative number in this situation. I just don't know which it is. It turns out it won't matter. It'll end up giving us the same answer either way. Now I want to find tangent. Well, in order to find tangent, I need to know the opposite over adjacent, so I need to know what this opposite side is. And so I'm going to use the Pythagorean theorem. I know that x squared plus this unknown side squared has to equal 1 squared. So I'm going to call the unknown side, I don't know, I'll call it b, like this is a and b and c, for example. So I'm going to say x squared plus b squared is equal to 1 squared. So b squared is equal to 1, 1 squared is 1, minus x squared. So b is equal to plus or minus the square root of 1 minus x squared. Now when I look at my picture, I notice that my opposite sides in both of these quadrants is positive. So really I don't need the negative value. I'm going to choose the positive value here. So this is the positive square root of 1 minus x squared, and this is the positive square root of 1 minus x squared. Now I want to know what tangent is. Tangent is opposite over adjacent. So notice that if x is positive or negative, my actual ratio of opposite over adjacent looks exactly the same. So y equals tangent of inverse cosine of x, which is equivalent to the square root of 1 minus x squared over x. So this is the algebraic function of x that is equivalent to the angle that I just got here. So, or I'm sorry, it's equivalent to this trig function. Now why would I want to change it from this form into this form? And you might be skeptical that these are even the same thing. I'm going to show you that they are in just a minute. It turns out that in doing calculus, it's a whole lot easier to do calculus on the function written in this form with an x squared and an x in it than with a tangent and an inverse cosine in it. This is much more usable for calculus. So we're just changing something from trigonometric form into algebraic form for purposes of taking a derivative or an integral in calculus, some things that you do in calculus. But how do we even know that these are the same thing? we're going to actually graph them and show that their graphs are the same. You can see here I have graphed tangent of inverse cosine of x, and it's kind of an odd looking graph. Now the question is the graph of the other function exactly the same as this one. So I've actually already typed in the other function. Here's our function that we found. I unchecked it so it wouldn't show, but I'm going to check it now so it shows and push enter. And you can see that this graph exactly covers the first graph. So they're right on top of each other. So these two graphs are exactly the same. The functions are exactly the same. It's very odd to think that these two functions are exactly the same, but this is a useful way of rewriting as a rational function, or rewriting in an algebraic form something that is in trigonometric form. So that's the purpose of this. Okay, then the last part is a couple of concept questions. We've learned that inverse functions undo each other. Why does the inverse function undo the cosine function but not the sine function in the example below? So I'm going to expand this a little bit so make it a little easier to see. Okay, so we have cosine of 2 pi over 3 is negative 1/2. Inverse cosine of negative 1/2 is equal to 2 pi over 3. Sine of 2 pi over 3 is equal to the square root of 3 over 2, but inverse sine of square root of 3 over 2 is equal to pi over 3, not 2 pi over 3. So why is it that we can undo cosine of 2 pi over 3 with the inverse function, but we can't undo sine 2 pi over 3 with an inverse function? So here's the explanation for this. So let's draw 2 pi over 3. 2 pi over 3 is 2 times pi over 3, 2 times 60, it's 120 degrees. So it's in quadrant 2. 120, 2 pi over 3. Has a 60-degree reference angle, which means this would be square root of 3, negative 1, 2. So you can see the cosine of this angle is negative 1/2. When I do inverse cosine of negative 1/2, it gives me an angle that's in either quadrant 1 or 2. And since it's negative, I get a quadrant 2 angle back. Okay, so I get an angle back between 0 and 180, or 0 and pi. But when I do sine of 2 pi over 3, I get square root of 3 over 2, but when I do inverse sine of square root of 3 over 2, I get pi over 3. And why is that? Well, when I look at the problem, inverse sine of square root of 3 over 2, I have to think, I have an angle, I have a positive trig value. Positive trig values for inverse sine are always going to be in quadrant 1. So when I see inverse sine of square root of 3 over 2, I have to think, here's square root of 3 over 2. This is a 60-degree angle in quadrant 1. This angle is pi over 3. So when I undo square root of 3 over 2 for inverse sine, it's in quadrant 1. And that's because this was a negative trig value, which gives me quadrant 2 for cosine. This is a positive trig value. So this is negative trig value. This is a positive trig value, which gives me quadrant 1 for any angle. So for sine, cosine, or tangent, if it's a positive trig value, I'm always going to get quadrant 1. So it doesn't, even though sine is also positive in quadrant 2, that is not where the principal angle is located. The principal angle is between negative 90 and 90, or negative pi over 2 and pi over 2 for sine. So I cannot get 2 pi over 3. However, 2 pi over 3 is in the range of inverse cosine. So after saying all that, what would I write down? I would say that for a negative trig value, inverse cosine is going to give me a quadrant 2 angle. For a positive trig value, inverse sine is going to give me a quadrant 1 angle. So we're not going to get the same angle back. The question here, the next question here, if I can extend my page just a little bit, there we go, is when does sine of inverse sine of x not equal x? And this is a different question from question 1, because in question 1, I wasn't undoing, I don't know how to, well, because I wasn't doing inverse cosine of inverse cosine of 2 pi over 3. I was doing inverse cosine of 2 pi over 3. Anyway, never mind. It doesn't, it's not going to be the same question. Here I'm starting out by finding an angle and then taking sine of an angle. Here I was starting out by finding a trig value and taking inverse function of a trig value. So the question is, if inverse functions undo each other, when will this not equal x? All right, so we could try some values maybe. So let's put in a calculator page, add a calculator page, and say inverse sine of 2. Or did I do that backwards? I think I may have done that backwards. It's sine of inverse sine. Okay, there we go. I did that backwards. So we will erase this, and we'll just do another one. So it should be sine of inverse sine of inverse sine. Try this again. Sine of inverse sine of 2. It says domain error. Ooh, okay. Could I do something else? Is this always going to give me a domain error? Let's try -2. Oh, domain error. Okay. Let's try -1. I got -1. Let's try +1. Let's try 0. Let's try something in between 0. Let's try 1/2. 1 divided by 2. Okay, let's try -1 divided by 2. Okay, so this seems to always return the same value when I'm between -1 and 1, but not when I'm bigger than -1 or smaller than 1. And hopefully you're going, okay, domain error, what is the domain of the inverse sine function? The inverse sine function is only defined for trig values that sine can actually equal, somewhere between -1 and 1. So the correct statement would be when x is in the domain of inverse sine, which is between -1 and 1. Oh, or I should say, when does it not equal? When it is not in the domain of inverse sine. So when x is not between -1 and 1, there's our nice announcement again. When x is not between -1 and 1, then this would not be true. You'd get a domain error. But other than that, it will always equal x. Okay, there's some tricky problems. There's another example. I think that the video is called Tricky Trig Problems, that give you another problem like example 5 and another problem similar to either example 3 or example 4. So if you're looking for one more example of that would be helpful, that I would recommend that little video. It's shorter than this one.